Welcome to Pod Studio, level up your fluency from trending topics. Today we are going to talk about DeepSeek's efficiency and AI market shifts.
Welcome back to the Deep Dive. Today we're cutting through some of the hype around the big AI players. We're focusing instead on a newer name, DeepSeek, a Chinese startup that's making waves. They're basically promising to completely flip the script on the economics of artificial intelligence.
Yeah, it's a pretty bold claim. We're diving deep into how they're doing it, or at least how they say they're doing it.
Exactly. Our mission today, we want you to walk away understanding how this, relatively small company can claim such massive efficiency gains. And crucially, what does this actually mean for all the billions pouring into AI infrastructure, the whole GPU race?
Right, because the central claim here is, it's genuinely staggering. It really sets the stage. DeepSeek, they were only founded in 2023, just last year. And they're claiming they trained their open source model, DeepSeek R1, for a surprisingly low amount, just $6 million.
$6 million.
Using 2,000 NVIDIA H800 GPUs, which, again, sounds like a lot, but context is key here.
Okay, $6 million. You hear that number and immediately compare it to the incumbents, right?
Absolutely. It creates this cognitive dissonance straight away. Think about the proprietary giants. GPT-4. Estimates are around $80 million, maybe even $100 million, just for training.
Huge difference.
And Meta's Llama 3 needed something like 16,000 H100 GPUs, top-of-the-line stuff. Now, we absolutely have to stress what our sources emphasize. These comparisons are tricky, far from apples to apples.
Different models, different goals, different architectures.
Exactly. But even if you account for some, let's say, marketing spin or differences, the sheer scale of the claimed efficiency, that's what we need to dig into.
Okay, let's unpack this then. How on earth did a company with, fewer than 200 employees manage this? They're backed by Highflyer, that quant fund, right? But still, it's impressive. How's the market reacting?
Well, the market reaction was almost immediate and pretty explosive, actually, which, suggests the model itself performs well, at least on the surface. They released their model, get this, the day before OpenAI announced its massive Stargate project. Talk about timing.
Wow.
Bold move. And DeepSeek quickly shot up to become the #1 free app in the U.S. app stores.
That's a strong signal, that rapid adoption. And it wasn't just users. It spawned over 700 open source derivatives almost instantly. And maybe more telling, the big platforms jumped on it. Microsoft, AWS, NVIDIA AI, they all onboarded it pretty quickly. That speaks to stability and performance.
Right. So performance seems confirmed at a high level. But the core of our deep dive today is the how. How did they achieve this efficiency? It seems like they took a layered approach, optimizing different parts of the process, reducing costs for both inference, running the model, and training it.
Okay, start us off with the architecture. What were the key engineering choices there that cut costs so dramatically?
So the first big piece is the architecture itself. They leaned heavily on the mixture of experts design.
MOE.
MOE, yeah. We've heard that term floating around. It's not totally new, is it?
Not fundamentally new, no. But DeepSeek's implementation seems extremely efficient. See, their full model is actually enormous, 671 billion parameters total.
Whoa, but, and here's the clever part of MOE, for processing any single piece of input, any token, the model only activates a small fraction of those parameters, about 37 billion.
Okay, so most of the model is off at any given moment.
Pretty much. It drastically cuts down the computational load needed for both training and running the model later. And they claim it does this without really hurting the output quality.
That sounds like a fundamental saving right at the hardware level, like designing a massive office building but only turning the lights on in the rooms people are actually using. Is that a decent analogy?
That's a great way to put it, yeah. Very efficient. But beyond just the core MOE architecture, they also focused intensely on model optimization, using sophisticated distillation techniques.
Distillation. Okay, explain that a bit. How does that save money?
Essentially, distillation lets you transfer the complex reasoning capabilities learned by those huge, super expensive proprietary models and bake them into smaller, more efficient models, like their open source one. It's like transferring knowledge without repeating the entire expensive learning process.
Wait a second. If distillation is moving the knowledge, does that mean they're kind of standing on the shoulders of giants? Like, the real initial cost was borne by whoever trained the big model they're distilling from. This touches on those IP concerns mentioned later, right?
That is exactly the tension here. It's a critical point. Critics definitely argue that this heavy reliance on distillation raises questions like, where did the intelligence truly originate? And are the cost savings just, pushing the initial training expense onto someone else. DeepSeek also used reinforcement learning to boost performance, which apparently reduced the need for extensive, supervised fine-tuning, another traditionally costly step.
Okay, architecture and distillation. What about memory? Running these models, inference often gets bottlenecked by how much memory they need, doesn't it?
Absolutely. And that seems to be where one of their potentially most impressive technical innovations lies, memory efficiency. They developed something called the multi-head latent attention mechanism, or MHLA.
MHLA.
Okay, what does that do? In traditional attention mechanisms, the model needs to keep track of, well, basically all the interactions between different pieces of data. It consumes a huge amount of memory. MHLA seems to simplify this dependency, this memory requirement. The claim is it reduces memory usage down to only 5% to 13% of what older methods needed.
5 to 13%. That's huge. That feels like the ultimate lever for cutting inference costs, right? Less memory means you can potentially run these models on smaller, cheaper GPUs.
Exactly. So the model itself is designed for efficiency. But they didn't stop there. They also optimized things further down the stack. What changes did they make, say, in how they handled data or interacted with the hardware?
Yeah, let's go deeper into those system-level tweaks, the stuff that isn't strictly about the model's architecture.
Okay, so on the computation and data side, they used methods like mixed precision or low precision computation, specifically FT8 mixed precision.
FP8. So that means using numbers with less precision, fewer decimal places, basically, sacrificing a tiny bit of accuracy for speed and memory.
Precisely. For certain parts of the calculation, it can essentially cut the memory needed in half and potentially double the processing speed. It's a trade-off, but a very effective one for cost. And they were smart about their data diet, too. They apparently use an optimized reward function during training.
What does that mean, an optimized reward function?
It helps ensure that the expensive compute power, those GPU cycles, were focused primarily on the most valuable training data, trying to avoid wasting resources on redundant or low-impact information.
So really selective about what the hardware actually spends time crunching. Maximum bang for your buck, GPU-wise.
You got it. And this leads us to maybe the most unusual part, the system and hardware optimizations that go beyond standard practices.
Okay, now I'm intrigued. What did they do differently right down near the silicon?
Well, one really novel thing reported is their use of PTX programming instead of the standard CUD framework that most labs use.
PTX, I know CUD. What's PTX?
CDA is kind of an abstraction layer, makes GPU programming easier. PTX is lower level. It's the actual instruction set for parallel thread execution on the GPU. Using PTX gives DeepSeek's engineers much more direct, granular control over exactly how instructions run on the GPU.
Huh. Is that common? Why wouldn't everyone do that if it's better?
It's highly uncommon because it's way more complex. You need really specialized expertise. It's harder to work with. But the payoff is potentially hyper-efficient GPU utilization. If you're trying to squeeze every last drop of performance out of a limited number of H800s on a tight budget, that fine-grained control could be crucial.
Makes sense. And they improved communication between GPUs, too.
They did. They reportedly used something called the dual-pipe algorithm. It helps overlap the communication time between GPUs with the actual computation time more effectively. It's all about minimizing idle time in a big cluster, making sure GPUs aren't just sitting there waiting for data.
Okay, so if we pull all this together, the MOE, the MHLA, the FP8 precision, the PTX programming, it paints a picture of intense optimization. But let's circle back to that $6 million figure. There's still skepticism, right? What are the doubts analysts are raising?
Yeah, that's the big question. Is that number purely engineering reality, or is there some marketing math involved? The true cost is still unverified publicly, and there's definitely speculation that $6 million might rely on using a mix of GPUs, not just those H800s, but maybe including lower-tier, cheaper cards too.
So if they padded the cluster with older or less powerful GPUs, it brings the average cost down, but it also muddies the comparison, doesn't it? Makes it harder to replicate.
Exactly. It obscures the true hardware mix and the difficulty. And adding to the skepticism, some critics point out that DeepSeek hasn't necessarily invented brand new foundational AI techniques here. Instead, the argument goes they've brilliantly refined and combined existing ideas, MOE, distillation, low-precision computing, into an incredibly optimized package.
So iterative genius rather than foundational invention.
Perhaps, but you can't argue with the results, right? The efficiency gains seem undeniably real, even if the exact dollar figure is debated.
Okay, so regardless of the precise number, this leap in efficiency is happening. What does this mean for the bigger picture? For the future of AI investment? especially that massive spending on infrastructure.
Right. When executives and investors see these potential cost reductions, it triggers thinking about different future scenarios, particularly for the big cloud providers, Microsoft, AWS, Google, who are the largest buyers of these expensive AI chips.
What scenarios are emerging?
Well, the source material lays out three possibilities. First, there's the bullish scenario. Here, these efficiency gains make AI inference cheaper. But instead of spending less, everyone just uses more AI because it's more accessible. It's the Jevons paradox.
Ah, yeah. Cheaper resource leads to increased consumption overall.
Exactly. So demand elasticity is high. In this world, spending on high-end training for the next generation of frontier models stays strong, keeping overall CapEx high.
Okay, that's one view. What's the middle ground?
That's the moderate scenario. Here, the efficiency gains do lead to a decrease in spending, specifically on infrastructure, maybe by 30% to 50%. Cloud provider CapEx might drop from that projected $80–100 billion annual range down to maybe $65–85 billion per provider. But, and this is key, even that lower end is still 2 to 3 times higher than what they were spending back in 2023.
So even the moderate view still involves massive, historically high investment levels. That implies analysts still expect huge growth, just maybe not quite as explosive on the inference side.
Precisely. They seem confident that new applications and frontier model training will keep overall demand very strong. But then you have the bearish scenario. This assumes efficiency gains hit harder, maybe CI budgets get trimmed, and inference spending drops significantly. Here, cloud CapEx could fall further, maybe into the $40–60 billion range per provider. But again, context. Even this most conservative estimate is still 1.5x to 2x higher than spending levels just a couple of years ago.
That's crucial context. It puts the potential dip into perspective. It's still a massive market.
Okay, so amidst all this speculation about spending, what are the clearer takeaways? What seems generally agreed upon?
Well, first, inference is just one part of the puzzle, right? The biggest players, the ones driving those massive CapEx numbers, are still locked in a race to build the truly cutting-edge, next-gen models. Frontier applications are the big prize. Second, this DeepSeek example really highlights the intensifying battle between open source and proprietary models. That performance gap seems to be closing faster than many expected.
And there was a point about energy demand, too. Will all this efficiency actually lessen the strain on power grids everyone's worried about? Interestingly, the source material suggests probably not, at least not in the near term, say through 2030. The main bottleneck isn't necessarily compute efficiency itself, but the physical constraints on building new power generation and transmission infrastructure. So efficiency gains might just mean we can pack more AI compute within the existing or slowly growing power budgets. It doesn't magically reduce the overall energy needed if demand keeps rising.
Right, the physical infrastructure is the real gatekeeper for now.
Which brings us nicely to the playbook section. For executives, for strategists, for anyone listening.
Yeah.
The DeepSeek story isn't just about one company. It's about what it signals for the future of AI. That innovation is happening incredibly fast, it's iterative, and these breakthroughs can absolutely come from unexpected corners of the globe.
So how do we translate this efficiency earthquake into practical steps for our own organizations? What should people be doing?
Okay, the sources suggest 3 key strategic moves. First, prepare for cost disruption. Don't panic or overreact, but you absolutely need to start planning for a future where AI inference could be significantly cheaper, maybe even, say, 90% cheaper within a few years. Think about what that enables. Broader adoption, certainly, but also totally new competitive dynamics in your industry.
So adjust our internal cost models and start brainstorming what becomes possible when AI gets much, much cheaper. Okay, what's step 2?
Step 2 is more tactical. Monitor market signals closely. Keep a sharp eye on those cloud provider CapEx trends we discussed. Watch GPU demand, look at AI adoption rates across different sectors. If you start seeing that infrastructure spending genuinely slow down, even from the elevated levels we talked about, that's a strong indicator that these efficiency gains are really starting to reshape the broad economics of AI.
Be watchful. Got it. And the final step, this sounds like the most strategic one.
It is. Step 3, think beyond just productivity. AI needs to be a business model catalyst. Look, the real winners in this coming era of cheaper AI won't be the ones who just use it to cut internal costs or automate a few tasks. That's table stakes. The winners will be those who leverage this cheaper capability to fundamentally redefine what they offer. Think hyper-personalized customer experiences, developing entirely new AI-driven products, launching services that were simply unaffordable before. The cost floor is dropping, so you need to raise your ambition ceiling.
That's a powerful way to frame it.
Yeah.
So the big picture, DeepSeek really throws a spotlight on this profound shift. Efficient, often open source models are closing the gap with expensive proprietary ones much faster than expected, and that forces everyone from startups to tech giants to reassess their AI investment strategies.
Absolutely. And maybe a final thought to leave you with, something provocative to consider. If the cost of generating really high-quality AI output text, images, code, whatever, genuinely approaches near zero, where does the real value, the defensible moat, actually shift in the AI ecosystem?
Yeah.
Is it purely in the unique proprietary data used for training? Is it all about the specific application layer you build on top of the models? Or do those bleeding-edge frontier models, the ones still potentially out of reach for most, continue to hold the ultimate power?
That's a great question to mull over as this efficiency race keeps accelerating. Where does the value truly lie when the core generation becomes cheap? Lots to think about there. Thank you for joining us for this deep dive into the source material.